Hi, welcome to es301 Engineering Analysis. This is chapter 25, Runge-Kutta Methods. So here are the learning goals. At the end of this, you'll know the form of a differential equation. You'll be able to implement Euler's method to obtain a first-order solution to an ordinary differential equation. You'll understand how Hein's and the midpoint methods work. You'll know the general form of a Runge-Kutta algorithm for solving ODEs, and you'll be able to implement a fourth-order Runge-Kutta algorithm. So here I just want to quickly review what is an ordinary differential equation. So here I have written a differential equation, and this is an ordinary differential equation because we have the differential of y with respect to x is only a function of the variable itself, y, and one other variable, x. Right? So I want to point out that if I had some function, say y is equal to x squared minus x, and I was going to determine what dy dx is, well, dy dx here is going to be just simply 2x minus 1. It's not a function of both x and y. So although this is also an ordinary differential equation, the form that we're interested in are those that are a little bit more complicated. So for example, if I just had simply y squared equals x squared minus x, and you were to solve for dy dx, you would find out in that case it would actually end up being a function of both x and y. And that's where some of the interesting parts come in. Otherwise, this is generally just an integration equation. So differential equations that have the function y on the right-hand side of the differential is where most of the interesting stuff comes in. And this is sort of where you have positive and negative feedback, because the value of y is able to feed back into how y is going to change, either positive or negative. And so this is very important in control systems in particular. I want to differentiate what I mean by an ordinary versus a partial differential equation. Now, a partial differential equation says, well, if as dy dx, so now how does y change with a change in x? But when y might be a function of both x and y, but also z and w and some other variables. And this is a little bit more complicated. We're not going to be looking at partial differential equations. We'll be looking at just ordinary differential equations where we have a single independent variable x and a single dependent variable y that we're looking at there. Okay. Now, our general solution method is going to look like this. We're going to be stepping through y. As y steps through values of x, we're going to go and increase x. We could decrease x, but normally we'll be looking at increasing x. So we're looking at our next value of y, and we're going to be using our current value of y, and then we're going to be stepping a step size h, so that's how far in the x direction we're moving, and then we're going to have some weighting function phi that I have over here. So in general, I'm going to have it, so I have a plot over here of y as a function of x. So I'm going to start off, and this is my initial value of y. And then what I'm going to do is I'm going to take some step h. And what I'm going to do is I'm going to have to determine some sort of weighting function. I'm going to be adding to this current value to give me what my next value is. And maybe it's going to be there. And then I'll go ahead and take another step h, using this value of y, some weighting function to get myself to another point. And I'm going to go ahead and keep stepping through as I go through. So in general, what we're going to be looking at in this video is what the different functions phi are, the different ways we can determine what that weighting function is. So first I want to talk about Euler's method. This is the most simple implementation, and this is usually kind of your first go-to when you want to integrate an ordinary differential equation. And so again, here's my general form where I'm going to step through. My step size is h, and I've got some weighting function phi. And so what would be that weighting function? Well, remember, our first order Taylor series, if we wanted to go ahead and approximate what our value of y was at some future point, we used our current value, our first order derivative, and then the step size here, which would be delta x. So h here is delta x, that's my step size. So my function phi is just going to simply be the first derivative. So what would this look like? Okay, so here I have my axes. This is y as a function of x. And so maybe I'm starting off at this point here. And what I'm going to do is I'm going to determine what the derivative of my function is at that point. And I'll go ahead and step, and I'm going to go to there. And then I'm going to determine the derivative of that function, go ahead and take my next step and go there. And then depending on each time is that the derivative changes, I multiply that derivative by the step size, and then I'm going to go ahead and keep moving along as I go this way like that. Right? So there's going to be an approximation of what my solution is, and so I can go ahead and do this to my final value of x, however far I want to integrate it to. Now, my actual function may have looked like this. And so what it turns out is that since I'm taking the first derivative at this point, maybe I kind of overshoot it, and then maybe I undershoot it. And so your approximations of what that function should be are going to depend on how large your step size is. here's a picture from the textbook that shows as you decrease the step size, you tend to get closer to the true solution because you're not as likely to step away from the function before coming back to it and evaluating what the derivative is. So here we see when the step size goes from 0.5 to 0.25, we go from the black dots down to the blue dots, and we're getting much closer to the true solution with this black line. So one way, the Euler's method, you can always improve your resolution is by decreasing the step size. And you can do that until you start to run into round-off error on your computers. So if you're doing a number that's near machine precision, you actually can't get any smaller than that. So there's kind of the caveat with Euler's method, but usually you can get a pretty good idea with a pretty decently small size step size. The next method I want to talk about is Heen's method. And this is just a way to go ahead and improve on Euler's method. So let's go ahead and remember, Euler's method, I start off at this point, maybe this point right there, and I want to go ahead and I determine my first derivative at that point, and then I go ahead and just more or less shoot out and say, okay, that's going to be my next point right there. Heen's method, the difference is that we say we're going to go ahead and do this as an approximation. We're going to go ahead and say, okay, well, we think we're going to go here, but now let's go ahead and find out what the derivative is at that point that we guessed it at, using the derivative at this initial point. And then let's take the average between that derivative and this derivative here, and let's use that one. And so the derivative, if I was to go ahead and approximate, maybe then I'm going to end up at this point. So more or less, I go ahead and I take some sort of approximation, and then I correct it, go ahead and give it here. So the general form of these are called predictor-corrector method. Predicting where I go, I correct what my step was, and then I'm going to go to this next point. Now note, Heen's method, you can do a couple things. You can iteratively do this a couple times. So I took the average between my first estimate and what it was at the initial condition, and I ended up with a new approximation. I could go ahead and determine what the derivative is at there. I'd again take the average of that, and maybe that's going to go ahead and give me some third point, third iteration, fourth iteration, and you can go ahead and implement that several times until you say, okay, well, now I think I've got a pretty good idea that this is probably what my next value is, and then go ahead and step through the next time. The midpoint method is just a slight variation of that. So again, let's kind of think, we're starting off at this point, we've got a derivative at that point, and then we've got some step size h. And so what I could do is I say I'm going to come out to here. Well, instead of coming to that point, I'm going to go halfway out and find out what the derivative is at that point, use that derivative. Okay, so this is just saying instead of the average between the 2 points, I'm saying maybe the true derivative is something that would occur in between. I'll go ahead and use that. Now, one thing with the midpoint method is you can't iteratively correct it. You just implement it once because there's only going to be one midpoint, and that derivative is never going to change what the derivative is at that midpoint. So midpoint is just kind of another implementation. It's not necessarily a better or worse. It's just another way to go at solving this with an improved Euler method. So now I want to move on to the general form of Runge-Kutta methods. And in fact, both Euler, Heen's, and midpoint methods are all actually implementations of the Runge-Kutta method. So here's my general way to solve an ordinary differential equation, where I'm to go ahead and find my next value of y. I'm using my current value, a weighting function times my step size. Now here, the weighting function in all Runge-Kutta methods are going to be functions of x and y, my current value of x and y, and the step size. But usually they're kind of some complicated function, usually sort of a iterative function of it. So for example, this is kind of what they tend to look like. Here's my function phi, and I'm going to have these weighting terms, a's, and those are usually just some constant values, and then k is some function. And so this right over here, this k again can be a function of xi, yi, and the step size. And then often what we'll see is k2 is going to be a function of k1 and then maybe x and y and h. And since k1 is just a function of x, y, and h, it's still just a function of x, y, and h. What we find out is that it kind of feeds on the value of k1, k3 might feed on the value of k2, etc. And as you include more and more of these terms, you're going to go ahead and get a better approximation of what the solution would be. And so when we talk about Runge-Kutta methods, you might talk about first order, second order, third order, and it's the number of k terms that I'm including in my approximation. So I want to focus on the fourth order Runge-Kutta method. It turns out the first and second order methods are really just like the Euler method and Heen's method. Fourth order is a pretty common one that you run into. It does a pretty good job. So let's go ahead and look at what its implementation is. So here I have y sub I, next one says to be y sub I plus 1, little typo there. Y of I plus 1 is my current value of y, and then I've got this weighting factor of 1/6, Here's my functions k times the step size. This whole thing in parentheses is phi times the 1/6. And what are those values of k? So for the fourth order system, this is what they are. K1 is simply whatever f of xy is. That's just what is dy dx. Right? So I'm going to go ahead and determine that. And then for K2, what I'm going to do is determine what is dy dx at, well, here I'm going to go the halfway point, so sort of like the midpoint, but I'm also going to go ahead and change what my value of y is. So this is actually going to give me a midpoint method as well. So there's my weighting function K2. And then K3 is going to be weighted by K2, so this is feeding off of this one, feeding off of this one. And this last one here, sorry, another typo, it's from K4. K4 is feeding off of that function right there. So, and now I'm kind of evaluating it at the end. So that's kind of the general form that you do for a fourth order Runge cut. It's actually pretty easy to implement. So let's go ahead and implement this in MATLAB. So here I have a script written. It's actually fairly simple. So let's just go ahead and step through it. So I start off here at the top with my initial conditions. I'm just saying, initially I've got my value of y at x equals 0 is value of 1. There's my initial condition. I'm going to go ahead and do this till x goes to 10. And I'll do a step size of 0.1. So I'm going to go ahead and take 100 steps through here. So I'm going to implement this in a while loop. And I've got, well, y is less than its value. And then here I'm going to go ahead and find my values of k1 through k4. I'm using this function func. That's a function I defined myself. Let's come down here on the bottom. And here you can see it's a very simple function as an external function. Where now I have this function. This is what dy dx is. So dy dx is equal to the exponential of minus y over 10 minus x squared plus 2x. So again, notice that I've got a y and an x on the right-hand side. And so my differential equation, my ordinary differential equation, is both a function of y as well as a function of x. So coming back up here, each time I evaluate k1, once I've evaluated that, I can use that to evaluate k2, k3, k4, etc. And then here's my Runge kutta, where I'm just going to go ahead and increment my value of y. So I'm adjusting my value of y, and then I increment my value of x until I'm done. So pretty simple implementation for it. This is a fourth order Runge kutta. If I was to go ahead and run this for this function, this is actually what it looks like. My solution, the fourth order Runge kutta, are these red dots over here. And so again, I've got 100 steps and going 0.1 each time, so the little red dots are. And the true solution, or pretty close, which is blue one right over here, that's actually done solving MATLAB's got a family of solutions to do. There's one called ODE45, and you might want to go ahead and take a look at that if you go to MATLAB.doc ODE45. This is actually an adaptable step size, which we'll look at in a later video, an adaptable step size implementation of a Runge kutta method. But what you realize is this simple implementation that I did in about 6 lines of code does a pretty good job versus something that's built in through MATLAB. All right, so let's go ahead and review what we looked at. We saw that ODEs are solved by incrementing along the independent variable axis, and we've got some weighting function phi. We saw that Euler's implementation is a first-order Taylor series, and that's what it uses for the weighting function phi. Hien and the midpoint method improve Euler by using different derivative terms. Hien's go ahead and can be iteratively implemented using averages of the original and the step size. Midpoint just uses that at the midpoint. And we saw Runge kutta are a family of methods. They all have the same general weighting functional form, just these functions a and k. And we also saw Runge kutta methods in general iteratively build the weighting function for improved accuracy. That's what it means is K2 is a function of K1 and K3 is a function of K2.